Welcome back. In the previous lecture, we defined non-deterministic communication complexity. In this lecture, we're going to show how we can use this to link it to the problem of controlling or bounding the complexity, in particular lower bounding the complexity of extended formulations. And the first thing that we need to do in this direction is to define a problem for which we're going to use non-deterministic communication complexity. And so we're going to define the so-called FACE VERTEX problem. And it's defined as follows. We have a polytope that has some number of vertices and faces, the same way that we have described it before. I won't enumerate them all here. We don't need that quite yet. So the problem is as follows. For a polytope P, we're going to define a function from discrete space x and discrete space y to 0, 1. Remember, this is the basic setup for the communication complexity problem that Alice and Bob are going to play. So for a polytope P, we define the function FV for face vertex. I'm going to define the function FV that maps from faces cross vertices. These are the discrete spaces x and y that we saw in the previous lecture to 0, 1, such that FV of a particular face F and a particular vertex V evaluates to 1 if that vertex does not belong to the face, and otherwise it evaluates to 0. In other words, if the vertex is on the face, then it is 0. So this is the problem. This is the game that Alice and Bob are going to play. Alice is going to get a face F. Bob is going to get a vertex V, and we need to think about a non-deterministic communication complexity style protocol. In other words, our prover to give a proof or a hint that will allow Alice and Bob to either both accept or not the proof. So this is the basic problem that we're going to use, and we're going to show that it is linked to the complexity of an extended formulation in a very important way. So here is the fundamental result that we're gonna need, and provides us really with the key. So if P, our polytope P, has an extended formulation Q that has complexity R. In other words, Q has R inequalities. Then the non-deterministic communication complexity of the face vertex problem that we just introduced on the previous slide, the non-deterministic communication complexity of the face vertex problem for P is at most log R. In other words, the prover is going to have R proofs or R hints. So what is this? How are we going to use this? we're going to use this because this means that if we can now lower bound the communication complexity, we have a lower bound, therefore, on the complexity of any extended formulation. So some notation that we're going to use for the duration is my polytope Q, which is the extended formulation. I'll write it as xy such that cx plus dy is less than d. And I'm also going to, it'll be useful for us to keep track of what this affine map is from Q to P. Now, if Q has a representation like the way I've written it, the affine map is really just a simple coordinate projection. It's just selecting the first coordinates. But we don't always have to restrict ourselves to such a map, though it really comes without loss of generality. So in other words, I'm just going to let pi, which might be a projection or not, denote this affine map from an extended formulation Q to P. So let's get back to this lemma and let's prove it. So we're going to give two proofs, and the first proof uses the slack matrix. Now the reason that the slack matrix is natural is that the slack matrix encodes the matrix of the face vertex problem. Encodes the matrix of the face vertex problem. In particular, specifically, the support of the slack matrix S encodes the entire function fv, because remember that let's write this down. Recall, what is Sij? This is the slack of vertex j on inequality I. So it is equal to bi minus ai transpose x. And so this is equal to 0 only, this is xj, the jth vertex. This is equal to 0. That means that xj is on that face. And if it's strictly greater than 0, then it means that xj is not on that face. So that means that the support is exactly encoding fv. So by the lemma that we proved in a previous lecture, by Yanakakis' result from 91, we know that the extended formulation, or unextended formulation, unextended formulation with R inequalities, as we saw, it gives a non-negative matrix factorization of the slack matrix. It gives a non-negative factorization. S is equal to U V transpose, where R is the small dimension. So we're now going to show that the non-deterministic communication complexity is going to be at most log 2R. In other words, we need at most R hints per proofs. So we now show that the non-deterministic communication complexity is bounded above by log R. So let's write the slack matrix S as the sum of ui, vi. So remember that the ij component, as I've written it above, is face I, extreme point, vertex j. So instead, let me change my notation to help us remember that a little bit more by writing S of fv. And we can see what S of fv is going to be just looking over here. That is going to be, that entry is going to be exactly the f row of u and the v, little v row, column of v transpose, or row of v. So in other words, this is equal to uf dot product v, is only make sure the capitals are clear, v little v. Now, by virtue of the fact that we have a non-negative matrix factorization, we can ask, when is this element, when is the fv element of the support of the slack matrix S, when is that non-zero? When will its support matrix have a 1 there? Well, that's when, of course, this is positive. But when is the dot product between two non-negative vectors strictly positive? It's strictly positive if and only if there is at least one coordinate of u and v, the same coordinate. There's at least some I for which the ith coordinate of uf and the ith coordinate of vv is strictly positive. And this is again because of non-negativity, because we can't have any cancellation. So in other words, writing this out, by non-negativity of u and v, uf dot product vv is strictly positive if and only if there exists some index j, which has to be between 1 and r, since uf and vv, as I drew them, are just r-dimensional vectors, such that ufj and vj are both strictly positive. So let's see how this gives a communication protocol. And it's as follows. We can pretty much see what the prover has to do. The prover, recall, sees both Alice's x and Bob's y. In this case, the prover sees Alice's f, face, and Bob's v, vertex. So the prover sees f and v and announces index j, which is something between 1 and r. Therefore, going to give us communication complexity log r. When does Alice accept? Alice accepts. Remember that Alice is going to accept if Alice thinks if Alice's index f has a 1 in according to the corresponding hint, and Bob is going to do the same thing. So Alice accepts if and only if u f j is greater than 0. And Bob accepts if and only if vj is strictly greater than 0. And that's exactly the story. So we can see that they will both accept exactly when S of fv is strictly positive, which means the support of S of fv is equal to 1, which means that the function fv evaluated at little f and little v is equal to 1. And that's the only time that they're going to accept. So that is basically the proof. So what does this tell us? This tells us that we can lower bound the size or the complexity of an extended formulation by lower bounding the communication complexity. So we've just mapped it into a different problem. So rather than now trying to directly control the non-negative rank, or in some other way trying to bound the number of facets I need for an extended formulation, I now have something that only depends on the matrix P. I'm sorry, on the polytope P, namely this new game, our FACE VERTEX game for Alice and Bob. And we can try to lower bound the communication complexity. And that will through this lemma, imply a lower bound on the complexity of, on the extension complexity. By lower bounding the non-deterministic communication complexity of FACE VERTEX. And we're going to see how we're going to use this. Now, it's instructive to give a different proof that doesn't directly use the slack matrix. And both of these approaches have been used. And in fact, when in the subsequent lectures we talk about lower bounding the extension complexity of the correlation polytope, we're actually going to use a technique that doesn't go through the non-negative rank, as this proof did, but uses communication complexity in a different way, that uses the, and it will use something very close to this alternative proof of this lemma that I'm going to give. So I should mention that the proof that we just saw is essentially the same as the Yanakagi's proof. It critically relies on ideas there. This proof is due to Lovash. So here's another way to see it. So let's suppose that we have FV of a face and a vertex evaluates to 1, which again means, remember what FV is. It means that Bob's vertex V does not lie on Alice's face F. So is not in Alice's face F. So the key is the following. If the prover can announce some hint, which in this case is going to be a facet, an index, in this case, a facet G of the extended formulation, so that means that G can take one of R values. So G is an element of 1, 2, up to R. So if the prover can announce an index G that satisfies two properties, then the claim is that we are in business, namely that Alice and Bob can correctly decide whether they should both accept or not accept this proof. So such that two things have to hold. Property 1 is that there exists some YV, V is Bob's vertex, such that YV is not an element of the announced facet. Remember that a facet is defined by just one inequality, whereas a face is an intersection of facets. So property 1 is that there exists a YV such that YV is not an element of G. And it will be, let's just observe to get us used to thinking about this affine map pi that maps from Q to P. Note that what this statement is saying, this is exactly equivalent to pi inverse of V intersect Q, because pi inverse V intersect Q for us is all the pairs V comma YV that are in Q. I should probably clarify this here. There exists a YV such that V and YV is in Q, and V and YV is not in G. So that's equivalent. I can write it more compactly as pi inverse V intersect Q is not a subset of the facet G. So if it's not a facet, if it's not fully contained, it means that there is some element of Q that projects onto V. In other words, there exists some YV, so that VYV is in Q, but is not an element of G. Okay, so these things are saying the same thing. We're going to use this notation when we come back to give a proof of the correlation polytope. So it's useful to see the parallels. And then the second property is that for any xy in Q with x an element of the face that Alice has, then xy is in G. So writing this in, I can write this similarly with the notation pi as follows. Pi inverse of F intersect Q. So again, this is pi inverse of F intersect Q is any xy that projects back onto F. In our notation, any xy in Q such that x is in F has to be contained in G. So these are equivalent statements, what's in parentheses and what comes before. So if the prover can announce a G that satisfies both of these things, then the facet G of Q is a proof that V, Bob's vertex, is not in the face. In other words, that FV of FV is equal to 1. So it's worth reflecting on this. So if there's a G, that's one of the facets. If the prover can produce one of the facets, one of the R facets, such that 1 and 2, properties 1 and 2 hold, note that this means this can only happen if V is not an element of the face. And that tells us immediately that FV of little f, little v is equal to 1. And the key point is that Bob and Alice can each evaluate whether or not 1 and 2 hold. So this is the key, and the whole reason that this is called a proof, that G is called a proof, or a hint, is that both Bob and Alice can check 1 and 2. Whereas, of course, they can't by themselves check whether FV of little f, little v is equal to 1. And this is the whole point. So if we can do this, if this is the case, then this is again a second proof that the communication complexity is no more than log the number of hints required. In other words, log R. So what do we have left to do? We have left to show that if V does not belong to F, then indeed such a facet G of Q exists. Again, let's review. Remember, I said if a prover can find such an index, then we're in business. So we just need to check, we need to show that for any pairs V and F, where V is not an element of F, one of the R indices, one of the R facets that define the extended formulation is going to satisfy this property. So let's see this. Okay, so pi inverse of f and q is equal to all pairs xy in q such that x is in f. And just by definition of how we wrote our polytope. Because the projection is indeed just the first coordinates. The affine map is just the first coordinates. And the inverse of v is similarly all v comma y in q. So since v is not an element of f, we're interested in the cases where fv of fv evaluates to 1, then this implies that pi inverse of f and q has no intersection with pi inverse of v in q. There's a lot of notation here, but actually this is quite straightforward. So I encourage you to try to parse it. It's pretty straightforward here. Right, so if v is not an element of f, then this is what this means. And you can. So I've written out those definitions there to help with that. So an important fact is that if I have any face of p, then the inverse under pi of that face in q is also going to be a face of q. So in particular, f and v are faces. So fv, but this is true for any face. Faces of p, this implies that p inverse of f and q and p inverse of v and q are faces of q. And I'll leave this as an exercise to you. I recommend just tackling it directly. Write out if they're faces, then they're defined by intersection of facets, and just check that indeed it has to be that you can find a supporting hyperplane, supporting hyperplanes in Q that define, in other words, facets of Q that define pi inverse f of Q and intersect Q and pi inverse v intersect Q. So I encourage you to try to verify this directly. It's not too difficult. A more subtle point, which again feels intuitive, but is actually an important fact about polytopes that we're going to use, is that any face of a polytope is the intersection of facets that define it. So this is, again, intuitive and natural. It's saying in a three-dimensional polytope, the facets are the two-dimensional planes. The faces are facets, lines, and corners. So this is intuitive to picture, but it takes a little bit of work to verify in general. So we're not going to go in these details right now, but this is a standard result from polytopes. So how are we going to use it? What this latter fact tells me is that, or the facts put together tell me that pi inverse f and q is a face. And since it's a face, it's the intersection of some of the facets of q. And we said q has r facets, g1 to gr. Pi inverse f intersect q is the intersection of some of those. So it's the intersection of, say, gi1 and gi2 and up to gik. So some k of them, where again each il is an element of 1 to r. These are the g1 to gr facets. Okay, so now back to this property here. Since I have no intersection here, what does that tell me? So since pi inverse V in Q does not intersect pi inverse F in Q, well, that means that pi inverse V in Q can't be contained in all of these. There's got to be one which doesn't contain it. And otherwise it would, since I have equality there, then pi inverse V of Q would intersect pi inverse F in Q. So again, since we have no intersection, that means that it cannot, it meaning pi inverse V, might as well write that just so we're clear, pi inverse V in Q cannot be contained in each of these GIL. So there's one of them which doesn't contain it. So let's just, there's one of them. So there is at least one, and I'm just going to drop the index and just call it G. Maybe that's GI1, maybe it's GI2, maybe it's GI3. Call it G, such that pi inverse V in Q is not contained in this G. And you'll immediately recognize that this is property 1. And meanwhile, however, pi inverse of F in Q, well, we said that this is equal to this intersection, so it is certainly contained in every single one of them. So it's equal to GI1 and up to GIK. Hence, it's contained in every one of them, and in particular, it's contained in the one that we just called G. Pi inverse of F and Q is contained in G. And this was property 2. So that's our story. That concludes this second proof that says that if an extended formulation has R facets, then the communication complexity, the non-deterministic communication complexity can be no more than log base 2 of R. In the next lecture, we're going to use this machinery to give a lower bound on the extension complexity of the correlation polytope. We'll pick this up then.